Let us learn absorption by inorganic systems in UV spectroscopy. In UV spectroscopy, inorganic systems exhibit absorption due to various electronic transitions, most notably DD transitions in transition metal ions and FF transitions in lanthanide and acetinide ions. These transitions are responsible for the characteristic colors observed in many inorganic compounds. Additionally, some inorganic ions like iodide, bromide, nitrate show relatively high polar absorptivities in the UV region. Such absorptions arise from a charge transfer process in which the electrons are moved from one part of the system to another by energy provided by the visible light. Electronic transitions in UV visible spectroscopy, which are important, are N2 pi star, pi2 pi star transitions. Absorption in inorganic systems refers the process in which the inorganic compounds or materials absorb electromagnetic radiation, particularly in the UV visible and infrared regions, causing electronic or vibrational transitions within the molecules or atoms. This absorption can be used to analyze the composition, structure, and properties of these systems through techniques like UV visible spectroscopy, infrared spectroscopy, and atomic absorption spectroscopy. Spectroscopy is a powerful tool for unraveling the mysteries of inorganic compounds. It lets us peek into their electronic structure, vibrations, and magnetic properties, giving us the crucial insights into their behavior and reactivity. When electromagnetic radiation interacts with an inorganic system, it can be absorbed if the energy of the radiation matches the energy difference between the system's ground state and an excited state. This absorption leads to electronic transitions within the atoms, ions, or molecules. In UV spectroscopy, inorganic systems exhibit absorption due to electronic transitions within the material, particularly involving D and F electrons in transition metals and lanthanides and charge transfer transitions. This absorption leads to the formation of unique spectral patterns that can be used for identification and quantification of these compounds. Absorption spectroscopy is a powerful tool for studying inorganic systems. By analyzing the wavelength of light absorbed, researchers can identify the presence of specific compounds, determine their concentrations, and gain information about their electronic structures. UV spectroscopy can be used to identify the presence of both organic and inorganic compounds in a solution and quantify their concentrations quickly and efficiently. Absorption by inorganic systems can refer to a few different things, including adsorption, UV visible absorption spectroscopy, and precocious absorption. Absorption. A surface phenomenon where a solid support or adsorbent embraces gas or liquid molecules on its surface. Inorganic adsorbents include zeolites, carbonate adsorbents, metal oxides, microporous and mesoporous materials, and metal organic frameworks. UV visible absorption spectroscopy, a method used to study the structure and behavior of inorganic compounds, especially transition metals, lanthanides, and acetinides. Precocious absorption, the process by which inorganic nanoparticles are absorbed through the skin. This process can be studied in vitro or in vitro and in the skin of humans and other species as well as in the synthetic membranes. Ultraviolet visible spectroscopy for inorganic compounds. Ultraviolet spectroscopy is a study of the transition involved in the rearrangements of valence electrons. In the field of inorganic chemistry, UV-Vis is usually associated with DT electrons and colored transition metal complexes. Examples for inorganic compounds. Various physical inorganic adsorbents have been used for CO2 mitigation process, including zeolites, carbonic adsorbent, metal oxide materials, microporous and mesoporous materials. Activated carbon and carbon seals, metal organic frameworks, and chemically modified mesoporous materials. 4 types of inorganic compounds. In general, there are 4 groups of inorganic compound types. They are divided into bases, acids, salts, water. Note that these are the broadest categories of inorganic compounds. Now let us discuss the electronic transition that happens in inorganic compounds, inorganic materials. UV spectroscopy involves the interaction of UV and visible light with matter, causing electrons to move from lower to high energy levels, electronic transitions. In inorganic systems, these transitions can involve charge transfer transitions. These involve the movement of electrons between the metal ion and the ligand, often resulting in intense UV absorption bands. D and F electrons. In transition metals and lanthanides, electrons in the D and F orbitals can be excited, leading to characteristic absorption bands. The splitting of d orbitals in the presence of ligands, ligand field theory, affects the wavelengths of these transitions, creating unique spectra for different complexes. In the UV spectroscopy, inorganic systems exhibit absorption due to various electronic transitions, most notably DD transitions in transition metal ions and FF transitions in lanthanide acetonide ions. These transitions are responsible for the characteristic colors observed in many inorganic compounds. Additionally, some inorganic ions like iodide, bromide, and nitrate show relatively high molar absorptivities in the UV region. Such absorptions arise from a charge transfer process in which the electrons are moved from one part of the system to another by the energy provided by the visible light. Electronic transitions in UV visible spectroscopy, which are important, are N to pi star transition and pi to pi star transitions. DD transitions. These occur within d orbitals of transition metal ions. When a transition metal ion forms a complex with ligands, the degeneracy of the d orbitals is lifted, creating different energy levels. Absorption of UV or visible light can then promote an electron from a lower d orbital to the higher one, leading to the observed color. For example, the blue color of copper sulfate solution is due to DD transitions. FF transitions. Similar to DD transitions, FF transitions involve the promotion of electrons within the F orbitals of lanthanide and acetonide ions. These transitions are generally weaker and result in more subtle colors compared to DD transitions. Other inorganic ions. Some inorganic ions like iodide, bromide, and nitrate also exhibit UV absorption due to electronic transitions involving their valence electrons. Absorption spectra. In UV spectrum of an inorganic compound is a plot of absorptions versus wavelength. Specific wavelengths are absorbed, creating peaks in the spectrum, while others are transmitted. Identification. The position and intensity of these peaks are characteristic of specific compound and its environment, enabling qualitative analysis and compound identification. Quantification. The Beer-Lambert law relates absorbance to concentration, allowing for quantitative analysis for the compound in solution. Examples of inorganic systems in UV spectroscopy. Transition metal complexes. UV spectroscopy is a valuable tool for studying the structure and behavior of these complexes. Inorganic ions. Iodide, bromide, nitride have been shown to absorb UV light. Inorganic minerals. Many inorganic minerals, such as those used as pigments, having characteristic UV absorption spectra. Types of absorption. UV visible absorption. This type of absorption spectroscopy uses ultraviolet and visible light to study the electronic transitions of molecules, especially those involving electrons in valence orbitals. Infrared absorption. Infrared spectroscopy focuses on vibrational and rotational transitions within molecules, providing information about the types of bonds present and their vibrations. X-ray absorption. X-ray absorption spectroscopy is used to study the electronic structure of atoms and their immediate environment. Electronic absorption. It involves transitions of electrons between energy levels within an atom or molecule, typically in the UV visible region. Vibrational absorption. It involves changes in the vibrational modes of molecules, typically in the infrared region. Atomic absorption. It occurs when atoms absorb light at specific wavelengths corresponding to their energy levels, used in atomic absorption spectroscopy. Factors affecting absorption. Solvent, concentration, pH, and temperature can all influence the position and intensity of absorption bands. Several factors can influence the absorption of light, which includes concentration of the absorbing substance. According to Pierre's law, absorption is directly proportional to the concentration. Path length of the light beam through the sample. Similarly, Pierre-Lambert law states that absorption is directly proportional to path length. Nature of the absorbing substance. Different molecules have unique absorption spectra based on their electronic structure and the types of transitions that can occur. Spectroscopy techniques. UV visible spectroscopy. It is used to analyze the electronic absorption of compounds in the UV visible regions, providing information about their structure and the electronic properties. Infrared spectroscopy. It measures the absorption of infrared radiation by molecules, revealing information about their vibrational modes and functional groups. Atomic absorption spectroscopy. It analyzes the absorption of light by free atoms, used for quantitative analysis of metals and other elements. Applications of inorganic analysis. Identification and quantification. Absorption spectroscopy is widely used to identify and quantify the presence of inorganic compounds in various samples such as solutions, solids, and materials. Structural characterization. By analyzing the absorption spectra, researchers can gain insights into the structure and bonding of inorganic molecules and complexes. Monitoring reactions. Absorption spectroscopy can be used to monitor the progress of chemical reactions involving inorganic compounds, providing information about the reaction kinetics and mechanisms. Qualitative analysis. Identifying the presence of specific compounds in a sample. Quantitative analysis. Determining the concentration of a compound in a solution. Analytical chemistry. It is used for identifying and quantifying the presence of inorganic substances in samples. Material science. It is used to characterize the properties of inorganic materials such as nanoparticles and thin films. Environmental science. It is used to study the UV visible absorption of inorganic ions in natural waters. It is used to analyze the levels of pollutants in water and wastewater. Chemical reaction monitoring, following the progress of chemical reactions over time. Examples: transition metal complexes. The absorption spectra of transition metal complexes often exhibit characteristic bands in the U-visible region due to DD transitions and charge transfer transitions. Lanthanide and acetonide ions. These ions also exhibit unique absorption spectra, which can be used to study their electronic structure and properties. Inorganic nanomaterials. Absorption spectroscopy is used to characterize the electronic and optical properties of nanoparticles, including their surface functionalization and oxidation states. Transition metal complexes. Many transition metal complexes exhibit characteristic UV-visible absorption spectra due to DD transitions. Inorganic ions. Iodide, bromide, and nitride ions have significant UV absorption in natural waters. Nanoparticles. The absorption of light by nanoparticles can be used to determine their size, shape, and surface properties. Two-dimensional materials. Materials like molybdenum disulfide and tungsten diselenide show absorption in the visible, UV visible, and infrared regions, making them suitable for various applications.